Introduction to Statistical Learning, Chapter 9. We're in the applied questions. I think this is the second to last question of the chapter, working with support vector machines. And here is question 7. We'll just kind of go through it here. So we're working in the auto data set, and the first thing that we're going to do in part A is to create a binary variable where we are taking gas mileage, and if for a particular vehicle, actually let me just pull up what this looks like here, maybe not all of it, so you can get a sense for what the data set looks like. Okay, so we have our data here, auto, and I'm just calling it D, and we have sorry to do this. I'm just going to clean this up a little bit. Okay, so we have our data set here that is different, features of a bunch of different vehicles, such as miles per gallon, cylinders, etc. And the first thing that we're going to do is we're going to create a binary variable that assigns 1 if miles per gallon is above the median gas mileage for all of the cars, and a 0 if it's below the median. Okay, and so this is the code that I use for that. So I'm calling that that new variable. I'm just calling it Z for ease of typing here. But now you'll notice that if we that's not what I wanted. I wanted this. Now we have Z over here, and it is assigning 1 or 0 based on whether or not a particular car is above or below the median gas mileage. Okay, so that's what's happening now. Now in part B, we're going to fit a support vector classifier, and we're going to try different values of the hyperparameter cost, and you'll see where that comes in here. We'll look at the cross validation that is associated with it. So to do this, we first need to install and load the E1071 package, and then this will be our code to run our linear support vector classifier. So I'm using tune, and I'm telling tune that I want to run a support vector machine, I want Z as a function of, and I've just selected these variables. You could use different variables or all of them. I just use these ones, and I'm using data D with a linear kernel, and then the way that we get to test a bunch of different cost values is to say we want ranges, and what ranges, or what hyperparameters do we want to test ranges of? Well, it's a list, and here we have cost, and so we'll try all of these different values for cost. Okay, and tune automatically runs tenfold cross validation, and this is what we come out with right here. And so we see that the best cost is 100. I'm actually going to rerun that for a second. Yeah, so this is interesting. Let me just run it one more time. Yeah, okay. The 100 was incorrect. I was messing with the code, and I was just making sure that this was actually steady, consistent from run to run. So, okay. We'll come back to this later, or to what our best parameter was for cost. But now in part C, we're going to do a very similar thing, but instead of using a linear kernel, we'll use a radial kernel as well as a polynomial kernel. And now we're testing different values of the hyperparameters. So for the radial kernel, we have basically the same code, but now in the ranges, not only are we trying different costs, we're trying different gamma values, And again, tune runs the cross-validation and tells us which one performed the best. And here we got a cost of 10 and a gamma of 1. And I'm just going to run this again for the same reason. I'm not sure if I had messed up the code at some point and forgot to rerun this. I'm going to, okay, there we go. Let's see. So yeah, so we get, that the best parameters were cost 10 and gamma 1. And we could isolate it here. Each one of these rows is a different model, a different combination of a cost and gamma value. Okay. And then also for polynomial, we do the exact same thing, but instead of doing cost and gamma as our ranges, we have cost and degree, right? Because polynomials come in different degrees, okay? And so here we have our best performing model again. Run it just to make sure I didn't screw anything up. And then in part D, we're going to make up some plots to back up our assertions. I'm not really sure what assertion we've made here. I don't really know. But anyway, so what I have done here. Okay, so previously, so we'll look at each of the different types of kernels. So first we did linear, and so what I'm doing here, instead of, so above we were using the tune function, and here I'm just going to straightforwardly use SVM with a linear function, and then for cost, I will use from the linear model above, I will use the best parameter for cost. Okay, so hopefully you see how I did that. And then that will assign the cost value to the best model that we already found. And then I just plot these. I'm sure that there's, a fancy for loop that I could run to make this, a little bit nicer, but, and I know you're supposed to use, things like for loops when you're repeating code, but sometimes I actually like to repeat code. It makes it more straightforward what's going on, although you increase your chances of errors, perhaps, or typos. But that's neither here nor there. So, so we have, 6 different plots, and I'm basically doing something like pairs plot, where I'm plotting each predictor against the other predictor, and just kind of seeing how, how the data lays here. Okay, and you can scroll through these. So here we have horsepower and displacement as the first one, and you see how it's doing. It's doing reasonable. There's quite a few errors in here. So, and you can scroll all the way down. But I repeat that for the radial as well as the polynomial kernels. So your plots will look different, no doubt, depending on what you regressed on here. I don't know if regress is the right word, but what you used as predictor variables. But that is that.